Hello, everyone. Today, I want to give a presentation about our paper with the title of What the Eyes Can Tell, Analyzing Visual Attention with an Educational Video Game. Here is a brief introduction about me and my colleagues. The game we based on to conduct this study is called Mission Hydrosign. Mission Hydrosign is an educational game teaching players water science and critical thinking. There are 6 units in Mission Hydrosign. However, players in this study only played through Unit 2. The primary goal of Unit 2 is to teach players navigate in a 3D virtual environment by reading topographic maps. Here is a small video to give you a general idea about how Unit 2 looks like. Within this unit, we selected a task called Find the Team. The players must use their knowledge of topography to meet with non-player characters in a specific location. The key point here is to identify the pathway between two mountains, which is marked by the red box. In this scenario, players can only refer to a map, the surroundings, the previous dialogues to find the correct destination. The instruments we used to collect self-reported expertise levels are demographic interview, topographic knowledge assessment, and the navigation experience questionnaire. The outcomes from those instruments will be used in later analysis combined with gaze metrics. Additionally, we also included 2 play measures, eye-tracking data and game logs. We used a Tobii Pro Lab to generate gaze metrics and visualization. We used the game logs to calculate how long players spend to complete the task. In the following 2 sections, we found 2 gaps identified from previous studies. One primary gap we are trying to close is about the learning dashboard design and development. The first thing I want to talk about learning dashboard is why it's a necessary component along with the educational game. Previous studies found that visual displays are critical to sense making because humans can process large amounts of data if they are presented in meaningful ways. Furthermore, visualizations are often the only reasonable approach to analyze data to know about the underlying process and the relations. Using such information, feedback can be provided to help users enhance their engagement and achievement. However, how to design and develop such learning dashboard is still a major challenge in the field of education. I listed some primary gaps from previous pieces of literature. Generally speaking, this topic is in its young age. Among this list, the gap we want to explore and try to close in this study is the bolded item. Few studies talked about the availability and the feasibility of adding visualizations from eye tracker devices into the dashboard. Another gap we are trying to explore and talk about is intelligent tutoring system. Basically, intelligent tutoring system provides timely and appropriate feedbacks to players during gaming procedure based on scores measured by stealth assessment. Stealth assessment automatically collects and measures players' capabilities without interruption. For our pilot study here, we are curious about whether the eye trackers can be one of the major data sources provided to stealth assessment, or in other words, can the gaze metrics provided by eye trackers reflect or measure players' competences? Based on the gaps I mentioned in previous sections, we framed 2 research questions as you can see in this slide. For our experimental settings, we recruited 9 students whose educational background is in the range of 6th to 8th grades. Each student played the game individually in a laboratory environment. Around 40 hours of eye tracking videos were recorded for later analysis. After knowing our experimental settings, we then decided the standard we based on to divide the performance groups. The standard comes from our latest field test, which happened in the spring of 2018 and consisted of over 500 players. Based on the testing outcome, we found that players who spent less than 3 minutes to complete the task have better learning outcomes than their peers. The next thing is to determine the areas of interest for collecting needed data. There are two AOIs. One is the map itself, which is marked by red color in the left picture, and the other is a box area where players need to go for completing the task, which is marked as green color. We involve the heat map and the gaze plot to do the examination. Then let's move on to the results section. We divided this section into 3 sessions. The first session is eye-tracking visualization observation outcome. Firstly, I'm going to illustrate the observation outcomes of a gaze plot. All 3 figures are from high performers. We summarize the following features of their gaze patterns. Their scanning patterns were generally compact. At first, their scanning lengths are long. After finding the possible correct location, their scanning lengths became shorter than before. High performers can ultimately find the correct destination after some trials. This slide shows gaze plots for low performers. The shape of the gaze plot was widely spread. They focused on a relatively larger portion of the map highlighted by darker colors representing high mountain ranges. Their number of gaze circles is much higher than high performers. The portion they scanned outside of the map is larger than their peers. After some hesitation, they finally turned their attention back to those incorrect mountain ranges. It seems that they are more likely to be distracted by unrelated but attractive materials. Compared with gaze plots, heat maps more clearly show which part is more viewed by participants. Right figures review high performance features. They have long fixation durations on the area near to the correct destination. They only paid attention to information associated with the task. They seldomly gazed at areas outside of the map. For low performers, we can see that they have a spread scanning pattern and they are distracted a lot by unrelated content. The outcomes we observed from heat map further confirm what we saw in the gaze plots. To further validate what we summarized in the previous session, we conducted hypothesis tests. We expect that hypothesis tests can tell us whether the aforementioned observed differences are accurately reflected by data, or in other words, whether the differences are statistically significant. So we created 3 hypothesis tests, which will be tested in the following session. Then we move on to the next session. First of all, I did some exploratory data analysis to know the dataset's properties. Based on the analytic outcome, we chose 2 testing methods marked here. One for normal distribution variables, the other is for non-normal distribution. The outcome tells us that the following 3 bolded variables have significant differences between 2 performance groups. To see more detailed information among those 3 variables, we draw box plots. Based on those plots, we can see that the high performers had a smaller fixation count on AOI 1, a higher average visit duration in checking via AOI 2, and spent less time checking the map. In summary, for the first hypothesis, part of it is proved to be true. For the second one, the variable which considering fixation and saccade together had significant differences between the 2 groups. For hypothesis 3, the outcome proved to be acceptable in the dataset. For second research question, we conducted a correlation test to explore the relationship between self-reported expertise levels and the gaze metrics. The method we applied is the Spearman algorithm. The table below only lists variables that have significant correlation with variables from gaze metrics. According to the table, science expertise, video game hours played per week, navigational ability, and navigational uncertainty have significant correlation with gaze metrics. For science expertise, based on the correlation outcome, we inferred that players with high science expertise use the in-game tools more efficiently than their peers. Additionally, they tend to use map later than students with lower science levels because they can find hints from other sources. If the science expertise provides factual and conceptual knowledge, we infer that the average amount of gameplay hours per week provides procedural knowledge. The factor causes the phenomenon that players with more game play hours used the map less than players with fewer gaming hours. The outcome related to navigational ability reveals that high navigational ability makes players more capable of finding hints from environmental surroundings and using map less than their peers. For navigational uncertainty, players with a lower score in this measurement have higher navigation experience. The correlation outcome tells us students with a higher navigation experience check the map less frequently and feel easier to decide the correct destination. For discussion section, we would like to provide answers to our research questions and point out limitations that guide our future research. Firstly, gaze plots and heat maps can distinguish players' gaze patterns in different performance groups. This conclusion is confirmed with both observation outcomes and hypothesis tests. Based on this conclusion, we claim that eye-tracking visualizations have the potential to be primary components in the learning dashboard. For the second research question, the correlation outcomes show that gaze metrics can reflect the player's expertise levels during gaming procedure. This conclusion shows that variables from gaze metrics are promising to make their contribution in building intelligent tutoring system. The primary limitations we identified in our article includes as following. Firstly, to make the conclusions more validated, we need much more data samples. Secondly, we should include more tasks in a single study, allowing us to gather gaze samples from various game actions so that we can predict the students' performances in various scenarios based on identified gaze patterns. Thirdly, we expect that our conclusions can apply to other 3D serious games that use navigational maps, but such expectations require further validation. So that is all for my presentation. Thank you for your listening.